Bismillahirrahmanirrahim. Hello everyone. This is the second method to solve Volterra integral equations, the linear Volterra integral equations to be more specific, and it is modified decomposition method. Let's call it MDM. Let's begin. We already know the Adamant decomposition method. So it will be easy for us to follow the steps of the modified decomposition method. Let's look at the steps. The first step, we let u of x equal to the summation n from 0 to infinity un of x, where u of x will be equal to u naught of x plus u1 of x, and so on. Then we substitute with the summation in the Volterra integral equation. After that, we write the modified recurrence relation. Before writing it, we split f of x into two functions, f1 of x plus f2 of x. By taking u0 of x equal to f1 of x and u1 of x equal to f2 of x plus lambda, the integration from 0 to x, k of x in t, u0 of t dt. We can get the rest of the values from the recurrence relation, which is u0 plus 1 of x equal to lambda, the integration from 0 to x, k of x in t, u0 of t dt, where n is greater than or equal to 1. Notice that u0 here is just a part of the terms which are not under the integration sign, and u1 of x is the rest of the terms that are not under the integral sign added to the integral part. Okay, uj of x, where j is greater than or equal to 2, is evaluated from the recurrence relation. This method is very good because you can use it to solve linear and nonlinear integral equation, and that makes it very powerful. This is the linear Volterra integral equation, u of x, in its general form, of course, equal f of x plus lambda, the integration from 0 to x, k of x and t, u of t dt. We want to use the modified decomposition method. So we split f of x into two functions, f1 of x plus f2 of x. And then by taking, for the recurrence relation, by taking u0 of x equal to f1 of x, and then u1 of x will be f2 of x plus lambda, the integration from 0 to x, k x and t, u0 of t dt. So we will get the rest of the values of the summation from this relation. Un plus 1 of x equal to lambda, the integration from 0 to x, k of x and t, un of t dt, where n is greater than or equal to 1. Okay? We need to apply the method on some examples. I solved some of them and you can try the others. Those are the rest of the examples. This is our Volterra integral equation. We are using the MDM, modified decomposition method, to solve it. First of all, we have f of x equal to 3x squared plus 1 minus e raised to minus x raised to 3. We need to divide f of x into f1 of x and f2 of x in a way that makes our solution comes easily, or the calculation that we will go through will be easy. So to think about it, if we take f1 of x, for example 3x squared, and plug it in here to get the value of u2. Let's try it together. 3x raised to 2, so f2 will be 1 minus e raised to minus x cubed. So the recurrence relation will be u1 u0 of x equal to f1 of x, which is 3x squared. Remember, those are optional. You divide them the way you want. u1 of x equal to 1 minus e raised to minus x cubed minus the integration from 0 to x e raised to minus x cubed plus t cubed. u0 of t is 3t squared dt. This will be equal to, we have here e raised to minus x cubed is a constant, but e raised to t cubed is in the integration. So when we derive t cubed, we will get, of course with respect to t, we will get 3t squared, and because it's multiplied here, we can write the following: 1 minus x cubed minus e minus x cubed e plus t cubed from 0 to x. Okay, and this is according to this law. When e of f of x is multiplied by f dash of x dx, we get the answer is e raised to f of x plus c. So it will be 1 minus e raised to minus x cubed minus e raised to minus x cubed multiplied by e, okay, e raised to raised to x cubed minus e raised to 0, which is 1, to make more simplification. We will disturb this component here and here. It will give us minus 1 plus e raised to minus x cubed. And from here we will get 0. And this is very good, because now when we write un plus 1 of x, which is minus the integration from 0 to x, e raised to minus x cubed plus t cubed un of t dt, where n is greater than or equal to 1, we will get this with the value of 0, right? Because if we, for example, plug in 1, it will be u2 of x will be equal to minus the integration from 0 to x e raised to minus x cubed plus t cubed u1, and u1 is equal to 0. So u2 will be equal to 0, and so on. That's mean un plus 1 equals 0, where n is greater than or equal to 1. And that will lead us to this conclusion, which is that u of x is equal to u naught of x, which is equal to 3x squared. And that shows us that we were lucky in choosing f1 of x and f2 of x. Okay. This is our second example, of course using MDM. Our f of x is equal to cosine x plus x sine x. Let's take f1 x is equal to cosine x. If we plug it here inside the integration, it will be easy to integrate. So let's try it. f2 of x will be equal to x sine x. Our recurrence relation will be u naught of x will be f1 of x, which is cosine x. u1 of x will be equal to x sine x minus the integration from 0 to x multiplied by u naught of t dt. That will give us x sine x minus the integration from 0 to x x cosine t dt. This is considered to be constant. Cosine t will be integrated as sine x sine t. So we'll have x sine x minus x sine t from 0 to x. We will have sine x minus sine 0. Sine 0 is 0. So that will give us x sine x minus x sine x, which is 0. And that will lead to the same conclusion, which is un plus 1 of x equal to minus the integration from 0 to x ut un of t dt. This will be equal to 0. So our u of x will be equal to u naught of x, which is equal to cosine x. This is our third example. It's pretty much the same. So by MDM, modified decomposition method, this is the f of x. So we want to choose our f1 of x and our f2 of x. We choose f1 of x according to the integration. Let's take e raised to x and sine x, as if we multiply it by x after integration, it might be vanished with those. So e raised to x plus sine x. f2 is the rest. So the recurrence relation will be u naught of x equal to f1. So it's going to be equal to e raised to x plus sine x. u1 of x is equal to f2 of x plus the integration from 0 to x multiplied by e raised to t plus sine t dt, which is the u naught of t. And this will give us x is constant, the integration of et is the same function, sine t, the integration of it is minus cosine t, and this is from 0 to x. Okay, this is from 0 to x. And this will give us exactly the same as those terms, which is minus xe raised to x and plus x cosine x, when substituting with x, so it will vanish. And the other part, which when we substitute with the 0, will give us x e raised to 0 is 1 minus cosine 0 is 1 too, and that will give us 0. So we can say, as the previous examples, that un plus 1 of x will be equal to 0 when n is greater than or equal to 1. Hence, u of x is equal to u0 of x, which what we want.